Okay, YouTube, in this video, this is my last one in which we're going to confront operating with trig form complex numbers, or complex numbers in trig form, and that is we're going to confront the operation of division. So how to divide numbers given that they are listed in trig form, that is complex numbers listed in trig form. So let's go ahead and get started by taking a look up here in the top left corner. We say let z1, or complex number 1, be this r1 times cosine theta 1 plus I sine theta 1, or in abbreviated form we could say our modulus is r1 times cosine I sine theta 1. So we have our length of our vector and our direction of our vector here, and we say our second complex number, we also have its modulus and argument, or length and direction. So we say if these two numbers are listed in trig form already, then we could say that their quotient, or z1 divided by z2, is simply this. This law basically states that we'll just take the two moduli and divide them in this order. So we say r1 over r2 is our new modulus. And we say instead of adding the two arguments, we could just go ahead and subtract them. So cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Or in abbreviated form, we could say that simply this all comes out to be the modulus is divided, module divided, and then cosine I sine of the difference between the two arguments. So let's go ahead and take a look at two examples. The first example we're going to do, we already have two numbers that are listed in trig form. I just want to show the simplicity of actually using this law to find the quotient between them. And then we'll actually do an example of two numbers listed in standard form, convert them to trig form, and then find their quotient using the same law. So let's go ahead and take a look at this first example here. We say z1 is equal to 20 cosine I sine of 75. And z2 is equal to 4 cosine I sine of 40. So if we want to find the quotient between these two things, we say, well then, z1 divided by z2 would actually be equal to the quotient of their moduli, so 20/4 in this case, or 20 divided by 4. And this would be cosine I sine of, now in this order, 75 degrees minus 40 degrees. So we'd say then this quotient overall, given that it's divisible, we say is 5 cosine I sine of 35 degrees, and this is totally an acceptable answer. As a matter of fact, this would just mean that our quotient is some number that is headed in like a 35-degree direction, which is be something maybe like this, 35 degrees, and 5 units out in that direction. We say is our r is equal to 5. So, you know, this is our quotient between these two numbers. Really easy to find. Okay, so what I want to do now is actually, we're going to find the quotient between these two numbers in standard form, and then we'll actually go back and convert them to trig form and find it again. So basically, if you've already got the gist of this from the first example, you can stop this video now. But this is just kind of to show you know, that you get the same thing if you do it from, you know, in standard form or in trig form. So this next example here, we say find z1 over z2. Let's go ahead and find it the, I like to say, the old-fashioned way. 1 plus radical 3i over, this is radical 3 plus 1i. So if we were to find, say, the quotient between these two things, the method for doing so when you have two numbers listed in standard form is to multiply by the conjugate of your denominator. So if we multiply by the conjugate of this denominator, what we end up with is this. We say, well, first of all, two complex conjugates come out to be the first term squared plus the second term squared. So really, this is all now going to be over, we say radical 3 squared, which is 3, plus 1 squared, which is 1, or over 4. Over 4. And then we say on top here, if we FOIL this out, we get, looks like radical 3, 1 times negative 1i is negative I. Radical 3i times radical 3, so radical 3 times radical 3 is 3, and then times I is I, so 3i. And then we say our last here, we say radical 3i times negative I is negative radical 3i squared. So cleaning this up a bit here, we say, well, negative I and positive 3i here in the middle, those combine out to be 2 i's. And then our positive radical 3 and our negative radical 3, well, actually this I squared would actually make this radical 3 positive, so we get two of these radical 3's. So 2 radical 3 plus 2i all over 4. And then this would actually reduce down, but let's split this apart. We get 2 radical 3 over 4, or radical 3 halves for this first part here. And then for the second part, we say 2i over 4, which is a half I. Half I. So this is not so bad. It's also not desirable if you ask me. So let's go ahead and convert these two numbers to trig form, which means we're going to need to know two things about these numbers. We need to know r. So we say r is, if you know you've been working with trig form numbers here, r is square root of x squared plus y squared, where x, of course, is a real part of our number, and y is the complex part of our number. And then we say the the argument, or theta, or the angle and standard position of the direction we're heading in here, we say is tangent inverse of y over x. So we know both y and x for both of these. We're going to go ahead and find them very, very quickly, and then we'll go ahead and use our law again for finding the quotient between these two things in trig form, not standard form. So we say z1. Okay, so z1 has an x value of 1 and a y value of radical 3. So we'd say our modulus of our first one here is the square root of 1 squared plus radical 3 squared, which is the square root of 1 plus 3, which is the square root of 4, which is, simply put, r1 is 2. So we're going to keep this in our back pocket. Now let's go find our argument. So we say theta is equal to tangent inverse of y over x. And our y value here is radical 3, and our x value is 1, looking at our complex number. But the tangent inverse of radical 3, should know this one, I'm just saying, but is 60 degrees. Now this is our reference angle, but given that 1 plus radical 3i is in the first quadrant, that is, 1 plus radical 3i, that's some number that is right 1 and up radical 3, which is slightly past 1 there. It's this number here. Basically what we're saying is this reference angle here, which is 60 degrees, is its own angle and standard position. So we say we now have the argument and the modulus. So our first number here, which is z1 in trig form, is 2 cosine I sine 60 degrees. So now we want to find z2. z2, we need its argument. You'll notice here that it has radical 3 for an x value and 1 for a y value. So when we find its modulus, it actually comes out to be the same thing as the modulus of the other one. We get 2. You can go check that with your r equals square root of x squared plus y squared. But we get cis. We want to find its argument now. So we'd say, okay, so theta in this instance, theta 2, this was theta 1 over here, theta 2 would be tangent inverse of y over x. In this case, we get a y value of 1 over radical 3, which of course rationalizes out to be radical 3 over 3. But we say tangent inverse of radical 3 over 3 is 30 degrees. So as an argument, so we say 30 degrees. So now if we want to find the quotient of these two things, here's what we essentially get. We say z1 divided by z2 would be this. z1, z2, we get 2 over 2 cosine I sine of 30 degrees. And in order to check this, what we could do is this. We could actually say this is 1 cosine 30 degrees if we write this out in an expanded form, plus I sine 30 degrees. Squeeze this in here. And we know that the cosine of 30, which is the same as sine of 60, is radical 3 halves. And then we say plus I sine 30. Sine of 30 is a half. And we say I. And you should notice, hopefully, that this is a very familiar number here. It is the same number we got when we had completed this computation or this operation in standard form. So, it's all a matter of personal preference, but what I'm going to tell you is this. It's really convenient to divide two numbers in trig form, because all you have to do is divide their moduli and subtract their arguments. That's the word I'm looking for. So, enjoy.